Okay, so for the demonstration number 2, we have the same person on the same rotating stool, but in addition to the system, we are adding this wheel, okay? And as you can see it on the figure that the person is going to hold the wheel from a kind of a shaft, and the wheel is free to rotate, okay? And the wheel is going to rotate as shown along this omega I direction. That means it will have a angular momentum in the direction of positive y direction. So this is the angular momentum of the wheel, and this is the initial case as well. Okay. The person is not rotating, not spinning, and neither the stool. So initially, the person has no angular momentum. Okay. What we're gonna do is we are going to flip the wheel upside down. Okay, so we're just gonna rotate it 180 degrees around the y direction. Okay, so make that positive y to negative y. So when you do that, the wheel will have, since it was rotating the same direction, this is gonna be the direction of the new angular momentum of the wheel. Okay, and as you can see, it's negative j hat, right? Upward is positive, downward is negative. But so if you think about the angular momentum, there's no external torque on it, so the angular momentum should be conserved for the system. The dashed line around like a circle is showing you what the system is consisting of. And since there's no torque acting on it, there's no external forces to create that torque, we say that the angular momentum is conserved. But initially, only the wheel had the angular momentum, right? So the person wasn't rotating, so that will go away. And final, the wheel has opposite angular momentum, so it's going to be negative direction. So let's just say initially we have positive L, okay? And final for the wheel we have negative L. So positive L plus 0 equals to negative L plus what? What do we need for the person to have so that angular momentum is conserved? If you do a quick math here, this is going to be simply 2L, right? Positive 2L. So the person should spin this way and with twice as much as the angular momentum the wheel has, so that it can compensate. And then on each side, right and left side, we simply have the same angular momentum because the angular momentum should be conserved. Okay, and in this process we are ignoring the friction and the wheel bearings and air drag, friction in the wheel bearings and the air drag, because we're assuming there's no external torques, right? So that's why this should be the case. And again, there's some math here, as I explained. It's going to be twice as much as that original one of the wheel. And the person and stand gain angular momentum equal to twice the initial angular momentum of the wheel, and in a direction equal to the wheel's original rotation direction. Okay. So if we know the moment of inertia for the person and stool, we can even solve for that angular velocity using this relation from the equation, from the angular momentum conservation. So it's very similar to the linear momentum conservation, but you can really see much cooler effects, which are not very intuitive, and it will probably surprise you. So hopefully now you understand the physics behind it. And there are several videos that I'm adding some demonstrations, so they're really cool. Try to think about it in terms of the background and theory behind it, and try to apply the equations. So there are a couple questions that I want you to answer just to make sure that the angular momentum concept is clear conceptually more than anything. I'm gonna skip this part. Some calculations here, but I will share the PDF with you so you can double check. And here's again, we have the summary. So what did we learn? The moment of inertia of an object is very important parameter that influences rotational motion. An object with the same mass but different moment of inertia values will rotate differently. When an object rolls without slipping, the bottommost point has zero velocity, the center point moves at the velocity of the center of mass, and the topmost point moves at twice the velocity of the center of mass. Think about that wheel that we considered when we investigate the combined motion. And if the net torque on an object is zero, the angular momentum will be conserved, just like the net force zero means the linear momentum is conserved. And if a pulley is not ideal, the tensions on either side of the pulley will not be equal. So that was really important, and hopefully you also see that in the one of the homework problems. And the angular momentum, like linear momentum, is a vector quantity. Okay, and if you ask me, angular momentum is more complex because of the cross products. It's resulted from cross product and makes it a little bit more less intuitive, or more not that. It's pretty less intuitive compared to the translational motions. So this is a quick supplemental example. I do suggest that you take a look at it. It kind of emphasizes that it's a vector form and the angular momentum conservation. There's a spinning disk. There are two of them, so you will see that application of quick angular momentum conservation. And this is as far as we will cover. So just like basics, but hopefully these are going to really help you in the next semester and in the future as well. So as a summary, rotational motion is very analogous to translational motion. When considering rotational motion, we describe the motion using the angular position, velocity, and acceleration. Those were the descriptors. When the angular acceleration is constant, we can develop simple relations between the variables, much like we did for linear motion with constant acceleration. We observe that there is a direct relation between the linear variables and the rotational ones. Just like translating systems, rotating systems possess kinetic energy as well. For a rotating system, we found that the mass alone is not the critical factor, but rather how the mass is distributed. The moment of inertia quantifies the distribution of the mass. For rotating systems, we apply the same fundamental physics laws, including Newton's second law and conservation of energy. For rotating systems, we focus on torques rather than forces. Also, we observe that for certain problems, it is advantageous to apply Newton's law in angular momentum form. And lastly, the motion of many real objects is a combination of both translation and rotation, so that's why we really need to understand both of them. Hopefully you enjoy the physics class as much as you can under the circumstances, but I hope you're gonna like those demos and hopefully they make more sense now because you know better, right? And if you have any questions, please don't hesitate to reach out to us.